Hi everyone, thanks for joining us today.
It does sound sophisticated.
Sophisticated, yeah.
With the ACE community for 3 years now.
Actually outlined everything.
Something that we find in the society.
First, talk about the problems that you're trying to solve.
All right. Hi, everyone. Thanks for joining us today. We are with you with another episode of Deep Random Talks. So we're excited to have Atif with us today. He's a researcher from University of Dublin. But we are going to talk about a very interesting topic today, which is how to make sure the embeddings that we use in natural language processing are explainable. And we talked about the relevance of that in a second as well. Awesome. So, topic of explanation for embeddings. Why do we care about this, Serena?
Well, so one reason that I care about talking about today is because before reading Atif's paper and getting a chance to chat with Atif, I'd never come across explainable word embeddings. I know that embeddings can be used to sort of explain the relationship between words in the English language, for example, the classical word to vec example. What is it? So man is to king as woman is to queen, something like that. So that helps us better understand English. But in terms of actually understanding the embeddings, I hadn't encountered this. So yeah, I think it's a really interesting piece of work. And I'm sure we'll get into more details about the ways that Atif actually measured the importance and the increased performance of explainable embeddings over, I guess, more traditional methods. And yeah, I think Atif really pioneered this work back in 2017, and this is pre-transformer. I think we've talked about transformers a lot on Deep Random Talks, and in general, the machine learning community is very enamored by transformers. And yeah, it'll be really interesting to hear how you can actually have strong performance without this transformer method. And yeah, Atif, it would be great if you could share some of the motivation behind working on explainable embeddings. I know that I think it was in 2016, GDPR came out and was put into implementation. And I think this relates to your motivation in exploring explainable embeddings with your paper, Eve.
Exactly. Yes, you got that right. I was working before that time period on semantics and trying to add semantics to decision making, and the motivation was coming from the fact that we have knowledge bases, Wikipedia, for instance. We use DBpedia, not directly Wikipedia, but so the idea was if we can add semantics to decision making, and that was kind of my motivation during my PhD. And in 2016, somebody heard me, I think in EU, and they decided to go GDPR, which sound like I was trying to say the similar thing, if not completely, but partially somewhere there was a match in the motivation to try to bring context to this decision making, and this is where I think this whole came out. Yeah.
So what you're saying is that your original problem statement was that, like, bringing semantics to decision making. But can you give an example? Like, what do you mean by?
Sure. So for that, we have to see the ideas of Web 2.0 to Web 3.0, and then adding semantics. So for instance, it all started from when you have a text and you want to anchor that, and then you have kind of like we call that as an anchor text, kind of a semantics that explains what that media is about when you're about to click on it. So that's kind of contextualizing it. Making that fast forward, I just thought, like, when we do classification and all those kind of things, the idea is, why are we classifying a certain thing in a certain way? So what could be an anchor to that would be the semantics associated to it. And that's where semantic web has been working, independent of the World Wide Web community or the free text community. Now, when it came to me, I was coming from the background of information retrieval, so I was more around free text, but I had certain motivation towards semantic web community.
When you're talking about a structure, things that come to mind is like ontologies and taxonomies, and different types of categorization and relationship building that we use. Is that roughly what you're talking about? So essentially combining, say, the ideas from ontology and taxonomy and such with unstructured text analysis that we normally do. Is that
Exactly. Back when I started my PhD, the dilemma was that most of the ontology works was on a very small scale data set. But when we talk about free text, we had huge volumes of data available to us. So I took upon this as a motivation, or I was curious if we can adopt some ideas from there and bring it to standard NLP community. And over there, I realized what I was trying to do was trying to add semantics to classification, if I might say that again. And that's where one of the problems that I came across during my PhD was kind of like, reputation management tasks. For instance, on Twitter sphere, there could be a damage to the company. Can we infer where this damage is coming from? This is one question, but the other question is like, is the tweet about the company or is it about someone else? And what aspects that does it talk about? And so, yeah, that was kind of the challenge, but nobody was putting it out there like, why is that related to the company, and how do you infer that it is related to a certain aspect of the business? This is where I just was talking with my supervisor, and we were discussing we should do some failure analysis to what of the the researches that we are trying to publish. And in terms of failure analysis, I just realized, how about like if you pick something from the semantic web community and try to do failure analysis in a more organized way, rather than going by the person who's sitting behind and just trying to understand as a technical person what went wrong. So I just crafted a model. I mean, at least I tried to attempt to do that back then, which could help me with failure analysis. But as a consequence, I realized that there was much bigger thing at play.
Throughout your PhD, and you graduated in 2015, right? And you developed this knowledge of building, these semantic models. And then when GDPR came out in 2016, in particular with this right to explanation piece, which is, again, the right to explanation is the right to be given as a regular person an explanation for the output of some algorithm. So it sounds like this really motivated you to sort of say, hey, can I actually do something with this related to word embeddings and related to Wikipedia in particular? And I was wondering if you could expand on that. I think I understand that Wikipedia is a text-based or free text format that you had worked with quite a bit in your PhD. And what made you decide to really start working on this, Wikipedia in particular, word embeddings in particular?
Here is the thing. I think a lot of the PhD candidates, when they finish with their PhD, would kind of agree with me, I suppose. We get very much bored with our own work. We don't want to touch it again. So I was under the same state of mind when I graduated. I really didn't want to touch my PhD ever again. I was bored to death. Let's put it that way, right? I mean, it was interesting, but when you do something for 4 years, there's a thing in you that you want to do something different. So I was doing something different, and I enjoyed that. I was doing social media analytics during my postdoc. Somewhere, when you do your postdoc, you have to lay down your own research agenda as well. And I went in to give a talk about my research early on, and there was interest from within where I was doing my first postdoc. It was at Insight Center in UCD. And some of the people become really interested in it. And some of the questions were very different from the way I got some of the questions in when I was doing my PhD, because it was more about getting my dissertation across, right? So it was more open-ended discussion that I enjoyed. And then in 2016, early on, there was a big thing on the block, which was GDPR and the right to explanation. And I had a chat with my mentor about this thing as well. And then there was the philosophy behind, and then we were just thrown away with it. And I could see the people whom I was working with, they were all ML experts. At least I would put it like this. I was inspired by them because they were more tuned towards ML models than compared to myself, because I was, somewhere in between IR and NLP, and I was trying to learn ML from them. But I have applied ML, but I haven't really, I just applied ML. I didn't know the foundations of ML. So I realized that there were concern about right to explanation and ML being a black box. And this is where I had certain discussions like around that what I've done could be related. And I realized that too. And that's where I think like this is an exciting thing because it is going to come into effect in 2018. And it was discussed in 2016 and everybody was curious about that. And I was like, all right, this is something exciting. And if I could make a dent around this, I could effectively learn a lot more about ML. I could effectively learn a lot more about how embeddings work. I could effectively bring some life to my boredom of my PhD topic as well. So that's where it was. Yeah.
Yeah, I definitely relate to that. Definitely, the ambition and interest to work on a slightly different problem after PhD is, or just generally any sort of intense work is something that I think a lot of people experience. But so okay, you decided to work on this problem, and initially, I assume you had some hypothesis about how you can tackle that problem. That they didn't end up panning out because it was just the beginning of the project. What was some of the ideas that you tried and didn't work?
Right. So during my PhD work, I was trying to gauge semantic relatedness, to say the association between concepts. Let's say one could be the query, the other could be the need, and trying to find how somehow a score for that. Then I just realized that, this equation wouldn't work. That what I proposed during my PhD because it was capturing a score, and we are not looking for a score. We are looking for association with anything which we can explain. I mean, semantic relatedness is one thing, but how much it is related to a certain concept, and there could be a number of concepts. So there were two challenges. One, which was about like how to come up with a better strategy rather than using the same equation that I had before. And second was more of a computational challenge, because when you have Wikipedia graph structure, how can you retain that into a memory? Because if you want to explain something and if you want to retain everything, so there was that as a challenge, and I encountered that during that period. And I realized that one way to get through that was sparsity of a matrix when we are trying to compare two entities and trying to, draw out explanation why they are related and why they are not related, whether we can run a coherence test or whether we can see how well do they cluster together and why are they clustering together, and as well as like query against an answer, which is information retrieval. I realized that, initially it was more like I wasn't really careful about how to manage the memory, and I encountered that very quickly. And I did not have an access to GPU as well. So those were the kind of the challenges that were major challenges. But of course, one thing is the modeling strategy, but I think like modeling strategy wasn't that difficult because a lot of the work that I've done during my PhD gave me an experience to solve that kind of, challenge. But I didn't encounter before a memory challenge. I did encounter, but I never encountered a memory challenge of such a scale where I was trying to retain entire graph structure of Wikipedia, which was humongous, into a memory, and then trying to make inference on it, and still keeping it explainable. Because if I were to drop that explainability bit, of course I can make concessions, but again, that would kill the whole purpose, whole goal of this research. So that was the challenge. How can I keep it inside the memory, irrespective of how much computational cost it takes without the GPU?
Interesting. So the first part of the sort of solution hypothesis that you had, other than the infrastructure issue, am I correct to say that you assume that relatedness means explanation directly, but that was an incorrect hypothesis? Is that a summary of what you said?
It was not enough. It was just not enough. It was something, but it wasn't enough. The equation that I had proposed during my PhD work, I think like that wasn't sufficient enough, because it whenever you come up with a model, you have certain examples in front of you when you're coming up with a certain equation. And my equation during my PhD was around how much two things are related to each other. And I was dropping why are they related to each other during that. Okay. Of course, I could understand it, but I was dropping a lot of it, which I could have retained, but because I was just blindsided, and then somebody came up with right to explanation, and then I realized, all right, yeah, that's interesting. Though when I was doing my own failure analysis, when I made the publications during my PhD, I was able to see them, but I was losing them from the model. So I would say the equation that I had a lossy ingredient in it, and I just wanted to bring that back into it.
Yeah, so I'm really curious to talk more about the methodology of Eve and how you applied this to Wikipedia, but sort of to level set a little bit. Wikipedia, I'm sure many people are familiar with it, but it's essentially made out of in links and out links, so an article can reference another article. I think an example you might use in the paper is an article about coffee could reference milk, and the article about milk could also reference coffee, because these two people often drink coffee with milk together. So these two articles are related. So there's articles, and there are also categories. So coffee and milk could be in the drink category. And yeah, from what you're saying, it sounds like it became throughout your PhD and work you've done, it became apparent that sparsity is very important. And you did end up applying this to Eve. Before
jumping to that, I'll first answer how did I capture the model, like how Eve actually works, right? So it was inspired from the pagerank equation, where you have citations coming into, and that was able to show like it works on entire internet scale, right? At least when it was proposed, and then afterwards there were variants of it. So that's from where I took the inspiration from to model it. So if I have a graph, for instance, whether it's a category graph or whether it's an article inlink/outlink graph, I could make use of a similar approach to PageRank and diffuse the score or propagate the score. But if I were to do it, for every two concept, I need to have a truncated version of it, and it should be quite fast rather than computing it online all the time, which is kind of the problem of the PageRank equation. So I come up with a strategy which was inspired from another paper called TrustRank, where you have the initial seed set and you propagate up to 5 hops or something like that, and then you just diffuse the score and obtain how the two concepts are related. But because I was retaining Node to have a label which would be like kind of a category, like they are both drinks, for example, in terms of like let's say coffee and tea, and they both contain caffeine, for example. When I was able to retain that, I also had a relatedness score on top of it. Then it makes it quite easy for me to make an explanation by saying, if whichever node is the most related one would contain a label on top of it. And that's how I can explain. So these two concepts, for example, are related to each other, and that's how they are related.
Let's say I'm using Eve. How does the explanation come about? I think you provided an example in line as what you were saying, but it would be helpful to just talk about an example just from end to end.
So we have to think about like what's the task at hand, right? I've mentioned 3 tasks in the paper, so I'll just pick one which might make sense. So we are looking for, let's suppose, if I throw randomly few concepts to computer and say pick the odd one out, we call that as a coherence challenge, which is kind of like how we build topic models, clustering, and all these kind of things. So, but it's coming from the coherence test. So which one is the outlier? If I throw, like, for example, 4 or 5 or 6 examples to computer, and then ask computer again, why do the computer think that out of the 6, 5 are coherent, and there is one which is odd one out? So let me give you a toy example. So let's imagine if I give 2 birds, which I know they are birds, but the computer doesn't. So for example, hawk and penguin. And then I give it another one, which is snake. And if the computer says hawk and penguin are related to each other and they're more coherent versus hawk and snake or penguin or snake, right? And snake. So if it could pick out, the odd one out, so it means it's an accurate model. That's the first goal. The second goal is, can the computer give an explanation by saying, hawk and penguin are related to each other because out of the top relatedness that I have with the concept, somewhere it mentions bird as bird families because of bird families. And then when it comes to snake, it says it is the odd one out because snake is more of a carnivorous animal than it is from the bird family. So if it can kind of say such things, it's an interesting insight. So imagine there could be, infinite, not virtually infinite applications to this. Imagine like there are like medical practitioners or medical situation. If we are able to say these two symptoms relate to each other and this is the reason why they are, because they are the symptoms of the same disease versus another symptom doesn't belong to that disease. It gives us insight. One of the problems with machine learning approaches was back then, like, are they generally applicable? So we picked up on 3 tasks. One was coherence test, which we thought like would be useful for topic modeling, which is more like a supervised learning method. The other one was around clustering. Are we able to cluster, closely knitted together? And then they are at a superior distance when they are not related to each other. And then each cluster is explained and it makes sense to the human who is reading it. And the third one was if we give computer a sort of query and then we ask computer to sort out the results, which kind of relates to information retrieval task when you have so many of those. And if it can pull the top end results that belongs to a certain need, for example, like if I'm asking for, a winner in physics, for example, or the physics, and then I'm trying to sort out Nobel Award or prize winners, right? And then is it able to shuffle or bring the top order to those who have won the award in physics, as opposed to others who have won on chemistry and other disciplines? If it is able to shuffle that could be interesting. And there was a funny thing that happened. I realized there was one wrong answer that we came across. It was somebody who it shuffled up in the top, for example. I don't remember exactly whether it was physics or chemistry or something else, but there was one person who came out somewhere in the ordering, and we thought like that person was related to another. Like, for example, if it was query around physics, he or she was the winner around chemistry. Then we tried to dig deep and we realized that's not the case. The person has won award both in physics and chemistry. So we were able to learn through explanations that even humans can have subjective opinions. And then it was I just realized, and because I prepared the data set myself as well, and my mentor also prepared them, we never realized that that person actually won two Nobel Awards, which was interesting. So just saying that the model is not accurate and we are losing some performance might not be the case. So if the machine is able to explain, we might just realize that we were wrong and machine was right. That could be also a possibility.
Yeah, it's very interesting what you're describing, having these 3 tasks to evaluate explainability and also how you can uncover things that I guess imply that humans do have opinions, like you were saying. And so in terms of the benchmarker baseline, so you compared Eve to 3 common methods, so word2vec, fast text, and glove. And these 3 methods, I'm not as familiar with fast text, but word2vec and glove, I believe, they sort of are like traditional language models that work on trying to predict words around a given word. And the methodology is very different from Eve. So 2 things. So on the one hand, these language models, so word2vec, fast text, glove, are very good at the given prediction task that's used to train them. But I think what you found is that when you actually evaluate the output embeddings from these 3 models and compare them to Eve, they don't come across as explainable as Eve when you look at discrimination, clustering, and ranking as your 3 tasks. So I find that very interesting. So that was my first point. And second point, Can you give a high-level overview of how you actually construct the embeddings? I'm super curious about that.
Right. So first, I'll pick one of the embedding methods. I'll just say word2vec, which because it's much more popular, right? So the idea of word2vec is to say two concepts or two terms or two phrases or two paragraphs, if we extrapolate that, but essentially two words, how similar they are, and it just gives you the score of that, right? And that's all. And it might, if you say, for example, a term, and then you want to pull out what are the other terms that are most similar to it, it will just pull those terms out, but it will not tell you more than that. So, for example, it won't tell you, for instance, why king and queen are similar to each other. It won't tell you that because it's losing that bit of information, because what you have is the vector that contains, for instance, like 100 or 300 dimensions of numbers, right? And then you just say -1 to 1, for instance. Those are the scores, and it's very hard to understand what does those scores signify. So that's where they lose explanation bit. Whereas when it comes to Eve, we build a structure using the nodes rather than having arbitrary 100 to 300 dimensions. We just have all the categories as a possibility of a dimension, all the articles as a possibility of dimension. And then wherever the two concepts intersect actually forms that as a vector for it. So if you don't have a sparse matrix in here or sparse vector, then it would be like virtually the summation of the number of articles that exist on Wikipedia plus the number of categories that exist on the Wikipedia would give you the overall dimension of a concept, right? But when you have the sparsity, in fairness, only a few entries where an article would hit to either other articles who inlinks to that article, that inlinks to it, or outlinks to it, or there is a mention of a direct category, and then there is an indirect category that comes through another category into that. So virtually, there are only few entries where there would be some deviation in terms of the score, as opposed to if you have like, you know, the dimensions being the summation of the hyperlinks and as well as the Wikipedia categories. So that's where the trick of maintaining the sparse matrix was quite informative, was quite useful. So when we think about word2vec, we think about finite dimensions. But when we think about Eve, I mean, it's in its originality, we don't think about fixed dimension. We think about relevant and related dimensions, which are maintained in a sparse representation. And then when we want to show something, we sort that by where there is a deviation in terms of how related the scores are. And then we just show them as a means to explanation. Now, this is why Eve is explainable. And for example, word2vec is not, because we are losing track of it. The next thing why Eve would work better than philosophically compared to word2vec. Word2vec utilizes the evidence of the surrounding terms, which is useful, right? When you talk about a paragraph. But if you have like things written in a neat structure or hierarchy, right? Word2vec directly doesn't apply to it, right? It's missing that. It assumes that for an embedding to work, you need to have free text representation or unstructured text. Whereas Eve makes use of, like, if you can give a structure, it would be able to, it will infer, more explainable representation of this. So for the task where hierarchy is important, Eve is more likely to outperform the algorithms or the embeddings where they completely disregard the hierarchy.
That's very, very interesting. So in general, even in this conversation, we started by talking about the motivation of explainability being ethics and regulations and such. But essentially what you're saying is for certain tasks, this kind of embedding will even outperform other methods through the explanation. And even, they're recently in a conversation about explainable information retrieval. Some of the folks were saying that they're interested in explainable AI, XAI, in the context of information retrieval, because sometimes the embeddings they use, even the more transformer-based advanced machine learning techniques, produce results that don't make a lot of sense. So they use explanations to identify where the model is failing, and then go back and fine-tune their large language models to essentially tackle those edge cases better as well. So I think there is a lot to be talked about around explainability beyond just ethics and regulation and the fact that we have to use it. So that's definitely a very interesting topic. But speaking of large language models, in the past few years since Eve came out, there has been an explosive growth of what people call large language models. As a physicist, that makes me very uncomfortable, because it feels like we're just throwing more and more and more data and computation into a box, and we just stare at it, and something comes out that obviously it's been quite impressive in terms of performance, but the trend just makes me very nervous. The trend of just over parameterized models with tens of billions and trillions of parameters used in these models, and the amount of data and computation and even like training time that is going into it, which makes it completely unusable for average users out there. But what are your thoughts around this trend that it has been happening that to a large extent also completely ignores the need for structure in the input data, and pretty much is assuming that if you just throw large enough amount of data at the model, it will figure out the structure on its own, and you do not need to explicitly tell it what the structure is, as you were doing in Eve. So what are your thoughts around that sort of direction?
Well, this is very, I would say it's subjective again. If we were to take on structure versus unstructured data, that's where we have the classic debate of databases and information retrieval, right? If you sign up to the structured, data, then you would be more towards databases community, because they look for structure and then they give structure, and then there's a way to question in a structured way and get the structured answer. So one short answers kind of thing, right? But when you're talking about information retrieval, we just completely disregard that and we say most of the data is anyway unstructured. So saying that we can find a structure for everything is impossible, right? So that's where there is a need for information retrieval and another NLP beyond databases. And I think that's why, because on the internet we generate so much volume of data and it's growing continuously. When it's user generated content, we cannot kind of hire people to give structure to those volumes of data, right? But when it comes to medicine, when it comes to scientific disciplines, when it comes to clearly knitted things where we take care of how we produce the data and how we consume the data, that's where structure is still relevant. So just saying that anything without a structure could outperform something with the structure, I think this is not a clear or believable answer even, right? The cost comes from whether we can give it a structure or not. That's where the issue is. When we don't have the structure, I think, the algorithms that operate without a structure, yes, they are the only option. So if they outperform them, that's fine. But when we have the availability of the structure and we are trying to say like, no, we don't need it, I think like it's not substantiated at least. I think it's coming from the trade-off. Like if you have it, use it. If you don't have it, then this is the next best thing.
So do you think that you would be able to achieve the performance of Eve and the explainability of Eve somehow using these more advanced machine learning models like Transformer? I think, there's a tendency in the community, to Amir's point, to, throw more money, more data into a model. And I think As a result, there's now the tendency to throw transformers at everything. I'm guilty of this in some research work I've done. It's sort of an easy way to get state-of-the-art performance on whatever task you're working on. So I'm curious, have you thought about how to use these models, if you can package them up in a way that would result in explainability that would be as good as Eve?
Right. So, okay, so I'll take a step back from it, right? I'll say what is there that we are missing from the models, right? From the other models. What we are missing is when we are trying to engineer the feature, either automatically or through DNN, for instance, right? Or we have the features. So let's talk about engineering the features through DNN, right? We are losing what's the label for each node that exists in the entire architecture. And my argument for the Eve is to maintain it somehow right then and there, instead of saying, I'll come back to it later, right? And that's where we say, all right, it is functioning fine, that's fine, then let's do, model agnostic explanation. My approach here is either we give some label to each node that exists in the architecture, somehow it needs to be correct, and then utilize that as an evidence to explain our results. If it's correct, the problem is solved, right? Now, the other option would be we don't have that. So we should have a model which could be computationally very expensive when it comes to practical setting. And then we are trying to make it computationally efficient. This is where we are losing some bit of it. So we are trying to use DNN, for instance, to lose that bit and make it more fast, for example. But if we know how it works, right, we can still retain the slow model that is able to explain, and then we have a corresponding efficient model that is losing all the bits that we have over there. And then when somebody desires an explanation, we can run it through the slow model that still works with it. And that's where I think Eve is adaptable to the likes of Word2Vec. So we worked on one of those things, but we haven't published it. It was more like an engineering thing that we were able to do, and worked, right? We were able to retain good performance, not good accuracy. Let's say, like, it was still able to outperform Word2Vec, Glove, and FastText. And FastText is actually the embedding model from the Facebook researchers. Just for the listeners, right? So it was still able to retain the performance, the accuracy, but it was clearly very fast compared to Eve. And it was purely like you have 600 or 300 dimensions, just like fixed dimensions, and it was operating in the same space. So if I were to say, can we do the same with transformers? I'd say, like, of course we can, right? The reason why I'm saying this, because I did this for a Word2Vec kind of a model for engineering purposes for one of our projects, and it really performed well and was at par how efficient Word2Vec is in terms of the computational complexity. It was matching that. So I would say, like, if it is adaptable in this space, we can still somehow find a way to do it with transformers, or perhaps come up with a new architecture where we somehow have an architecture that tries to label each node, and then there is an architecture that makes the prediction from that architecture. So if we can annotate the architecture that exists through an Embedding model, we can still use that as an evidence, as a back propagation or forward propagation, however, like we want to maintain it.
Yeah, so it's all very interesting, and we've talked a lot about, we talked entirely really about Wikipedia and these sort of graph style data sets. I'm curious, could Eve or a method similar to Eve be applied to tabular data? And this is really coming from a selfish place. I'm already thinking about how I can apply this sort of method to my work, and a lot of what I work with. There is an inherent structure in the data related to companies and their fundamentals, but most of the data really is tabular.
Right. Okay, so this would take me towards a bit of a philosophical position. So here is the thing: when we are applying STEM, there is a drive that we should also take into account of arts, humanities, and social sciences, and we should make it a combination of both, because the human is not something that we can easily explain or understand, right? There are sciences that do it for us, right? So I would say, even if there is a tabular data, that tabular data would be coming from a domain, right? And that domain could be business, that could be social sciences, that could be anything like that. So if we bring in somebody who understands that domain, with a little bit of work, they can somehow give us a hierarchy in which that tabular data could be arranged. And then we can make use of that in the same way as I did with the Eve. One of the problems that where we are applying, we are thinking to apply it, not we are applying at the moment, we are thinking to apply is and social sciences, right? On the problem of immigration or migrants versus natives, and the topics in which they are entrusted, and we are trying to arrange that into a hierarchy, and that hierarchy is going to be given to us not by the computer scientist, but more so can be given by us who are from non-STEM. And then we will utilize and see where does this exist. Of course, that would be like a tabular data, and then we can infer using that as well. So I'm just saying, like, when we have a tabular data, just step back and see where it's coming from. If it's coming from a domain, let's talk to that domain expert and ask, do you have a hierarchy here? Do you have a graph here? Can you discuss, can you detail it out? And they might come back and say, yes, we can generate one, give us 6 months of research time. But what happened is, we from computer science, we just totally disregard that or overlook this kind of a thing because we are under pressure from deadlines, or we might not even have reach over there, maybe because we are not in a collaboration with somebody who is from non-STEM. And that's where we make this oversimplification, and that's just try to get the point across or solve the problem without having the time at our hands to do it the way we want to do it.
Again, as a physicist, I love what you're saying as well, because a lot of the time building some sort of a logic in addition to the data that you're using can result in significantly better generalizability, which let's be honest, most of our machine learning models really suck at. It is very interesting. I guess the question that Serena asked and the answer you gave was very interesting because, in the case of general language tasks, like if you're working with a generic, question answering, like who's the president of whatever, there are probably enough text out there that relates all of these together that the large language model would come across it somewhere enough times that it, memorizes that. But for cases where we're talking about scientific relationships, about technical relationships that are not either, obvious, or they don't happen frequently enough for the language model to see and memorize them. In those cases, plus cases where there are, as you say, non-trivial business logic that can be added to the problem statement, in those cases, combining, language models and embeddings coming from, say, transformer-based methods or other methods that we use with, structured data that represents the logic and hierarchies that exist in the data can significantly improve the performance, especially in the cases where we are dealing with small enough data sets that even transfer learning is not going to do a lot of favor. So on that note, I think, unfortunately, we are out of time and we have to wrap up. And I'd like to ask 2 questions at the end in these sessions. One is, so we are going to provide a bunch of resources for the folks who are interested to read more or learn more about these topics, and they can take a look at it. There will be a link in the show description. But Atif and Serena, what are if people can only look at one resource to learn more about these topics, what do you recommend?
Should I go first? Right. If you're looking for, let's say, if you're looking for to know about Eve, for instance, of course, there is one publication of mine which you can look into, which will give you a different perspective as you were to see it through transformers or to back the way they are implemented. So you will get a different flavor of how you can model this. But the other thing the other thing that I want to say, I think like this is not said enough. I don't want to repeat myself in the sense like other machine learning people or the community talks about, stresses about. I want to give you a different answer from that. So what I want to say here is we need to read domain-specific articles first, because we don't understand fully what exists there in terms of how to explain something better. We don't appreciate that. What happened is we try to come up with a mathematical strategy, optimize something, and come up with a solution. Yeah, that's very popular. That's known. What is not known or what's underappreciated is if you're trying to solve a problem, go read some articles within that domain. If it's social sciences thing, if you're solving some problem from there, see what is the published literature from years and years and decades on it, and what model work and why they work, and what are the qualitative explanations that that community has for some model to work intuitively, and try to bring that into the model. Another thing is when you try to look into Eve, there is a different approach to it. And because Amir mentioned about he being physicist, here you can apply vector-based operations to say something. For example, I'll give you a motivation example here. If I say for a business context, let's suppose there is no importance of country. For instance, if you want to buy something, you don't want any influence of country. So what you can do is you can say, all right, these two concepts similar, but taking the difference from the vector that defines countries and nationalities. So you can get rid of something which is trivial to the business just simply by vector-based operations, which is interesting. And then you can see if that vector that you are pulling from is neat or not, because it's explainable. So the way here is to play around as, projections, as we call it, right? Vector projections, and just eliminate the dimensionality or the thing that you don't need. So this is another way of looking into it. So I'm just saying the two things, one to look for Eve in a paper, and the other is the intuition.
Makes a lot of sense.
Yeah,
Irina?
so my call to action for anybody listening and watching would be to really go and read Eve. There are some nice diagrams in there that describe how the embeddings were created. And yeah, I would encourage you to go through with either on your laptop or with a pen and paper and actually try to understand this intuition, because it's very interesting. And this relates to my main takeaway from this discussion and from the paper itself. So developer friends who are less familiar with machine learning, sometimes they'll ask me, oh, what is an embedding? And I always say, oh, well, it's really just a mathematical vector representation of some concept. You can describe a person by, if they have dark or light hair, that'll be a 1 or a 0. And if they're tall or short, 1 or 0, again, you sort of keep going. And I think in the machine learning community, there's a tendency to really use machine learning to learn embeddings. And I would extend that even to saying that there's the tendency to think if you're not using machine learning, then you're doing something wrong and your performance isn't going to be as great. But I think the Eve paper really proves that you can use a sort of like rule-based annotative method to create embeddings that are actually powerful. And I think sometimes it can be confusing to understand how embeddings are created in the machine learning space, but reading Eve, it becomes apparent that, it really is some sort of mathematical representation of some underlying concept. And it doesn't have to be extremely complex. There has to be some intelligence in creating the embeddings, but doesn't have to be anything too crazy and too difficult to understand.
Yeah, definitely. This conversation was a very good reminder for me that, in the past several years, we've been very much in the habit of, deep learning does the feature engineering for us. We don't need to worry about it. We can focus on other things. But the logic that was used in generating it, and that's causing a lot of problems. So this reminder that the logic that how the data was created and where it came from can significantly help us create models that perform better, even if we limit ourselves still to the deep learning models. But, really keeping a tab on where did we get this data, how was it generated, what was the business logic and domain knowledge is very important. So thank you so much for listening to us. Hopefully you enjoyed this conversation and learned something from it. Until next time.
Thank you.
Thank you.
Bye.